For 4.5 billion years, our sun has followed the same rhythm: rise, fall, flare, calm, repeat. A heartbeat so reliable that entire civilizations built calendars around it. But in 2026, scientists staring at 40 years of vibrations rippling through the sun's interior found something that shouldn't be there. The sun isn't just going through another ordinary cycle. Deep beneath its surface, something is rearranging itself. And nobody predicted it would happen this way. The sun produces enough energy every second to power human civilization for 500,000 years. It has done this so consistently that we built our entire understanding of stars around its example. So when astrophysicists say the sun may be entering a different mode of behavior, that is not a small claim. That is a claim that the star we thought we understood better than any other object in the universe might be quietly rewriting its own rulebook. I'm going to walk you through exactly what they found, why it matters, and what it means for the fireball keeping all of us alive. Welcome back to BigDataVault. Today, we ask a simple question with a very unsettling answer. Is our sun actually changing? Before we begin, if you're curious about the universe and the incredible stories hidden within it, consider liking the video and subscribing. Every bit of support helps us bring more fascinating discoveries to curious minds around the world. Now, let's begin. To understand what's shifting, you first have to understand what the sun actually is, because most of us have the wrong picture in our heads. The sun is not a burning ball of fire the way a campfire burns. There is no oxygen up there, no combustion in the traditional sense. Instead, imagine the sun as a mountain of pressure. At its very core, gravity crushes hydrogen atoms together with such unimaginable force that they fuse into helium, releasing a staggering amount of energy in the process. That energy then begins one of the slowest journeys in the known universe. A single photon born in the sun's core can take somewhere between 10,000 and 170,000 years just to fight its way out to the surface, bouncing between particles like a pinball trapped in the world's most crowded room. Once that energy escapes the surface, it takes just over 8 minutes to cross 93 million miles of empty space and land on your skin. So every sunbeam you feel is really a messenger, carrying news that started its journey longer ago than modern human civilization has existed. But here's the part most people don't know. This isn't a static process. The sun has an internal cycle, roughly 11 years long, where its entire magnetic personality flips. Sunspots come and go. Flares intensify and then quiet down. The sun's magnetic north and south poles even swap places entirely. For as long as we've tracked this rhythm, roughly 200 years of recorded solar observation, it has looked remarkably consistent, cycle after cycle. That consistency is exactly what makes this next discovery so strange, because for the first time, scientists have found the sun breaking its own pattern. Not on the surface where we've always been watching, but somewhere we could never see before. That question, what's happening in the one place we've never been able to observe directly, is what we're about to answer. And by the end of this video, you'll understand why some scientists think we may be watching the early signs of the sun evolving into something we've never seen it do before. You'd think that if the sun's activity was declining, we'd simply see fewer sunspots, and that would be that. That's the entire logic behind 2 centuries of solar science. Count the spots, chart the curve, predict the next cycle. But that assumption turns out to be dangerously incomplete. Here's the twist. Sunspot counts only tell you what's happening at the surface. And the surface, it turns out, may not be telling the truth about what's happening underneath. Think of it like judging how angry a pot of boiling water is by only looking at the steam escaping the lid. If the lid gets a little tighter, less steam escapes. But the water underneath could be boiling exactly as violently as before. You'd think less steam means less heat. You'd be wrong. The heat hasn't changed. Only what's allowed to escape has. That is essentially what a team of astrophysicists at the University of Birmingham discovered when they went looking for the truth beneath the sun's skin. Here's where the science gets genuinely strange, because the way we see inside the sun isn't with a telescope at all. It's with sound. The sun is a boiling, churning ball of plasma, and that churning generates constant, low-frequency sound waves, vibrations that ripple through the sun's interior, the same way an earthquake ripples through the earth. These sound waves cause the sun's entire surface to bulge and contract in impossibly tiny amounts, rising and falling by mere kilometers across a body that is over 1 million kilometers wide. By measuring those subtle oscillations, scientists can essentially perform an ultrasound on a star. This technique is called helioseismology, and a global network of instruments called BISON, the Birmingham Solar Oscillations Network, has been quietly recording these vibrations since 1987. That's nearly 40 uninterrupted years of listening to the sun breathe. Imagine trying to figure out what's going on inside a piano just by recording the specific hum it makes when nobody's touching the keys. That's essentially the scale of the achievement here. Using tiny sound signatures to map the invisible architecture of an entire star, layer by layer, without ever being able to look inside directly. So what did 4 decades of listening reveal? This is the part that should genuinely surprise you. You'd expect the sun's magnetic activity, the churning, twisting engine that drives sunspots and flares, to behave the same way, cycle after cycle, at roughly the same depth below the surface. That's what 200 years of surface observation implied. But the helioseismic data tells a very different story. With each successive solar cycle, the magnetic activity appears to be getting squeezed into an increasingly shallow band, confined now to roughly the top 1,000 kilometers below the surface. That might sound deep to you or me, but on the scale of a star whose radius stretches beyond 600,000 kilometers, 1,000 kilometers is barely a fingernail's thickness. The sun's magnetic engine, it seems, is being compressed closer and closer to the surface with every cycle that passes. Picture squeezing a tube of toothpaste from the very bottom. At first, the paste comes out steadily along the whole length of the tube. But if something starts pinching the tube from the middle, all that same pressure gets forced into a smaller and smaller space near the opening. The total amount of paste hasn't necessarily changed, but where it's being forced to concentrate absolutely has. That's roughly the picture forming of the sun's magnetic activity, not fading away, but being physically reorganized into a tighter, shallower zone. Now here's where it gets genuinely important, and where the sunspot counting method of the last 2 centuries starts to look outdated. Based purely on surface sunspot counts, the current solar cycle, cycle 25, looked like it was going to be a fairly modest, unremarkable cycle when predictions were first made. You'd think that means the sun's internal engine was running cooler than usual too. Wrong again. When researchers examined the high-frequency sound oscillations, the ones tied directly to the sun's internal magnetic engine, rather than what's visible on the surface, they found that the interior was behaving exactly as energetically as it had during previous, more active cycles. The engine underneath hadn't quietly powered down at all. It was running just as hard as ever. It had simply gotten better at hiding its intensity from surface observation. This is the equivalent of checking someone's pulse and thinking they're perfectly calm, only to discover their heart is actually racing beneath layers of insulation you didn't know were there. The surface told one story. The interior told a completely different one. And for the first time in the history of solar science, we now have the tools to know which story is actually true. Researchers involved in the study describe this as evidence the sun may be settling into a different mode of behavior. Language that, in the notoriously careful world of astrophysics, is about as close to raising an eyebrow as scientists get. Nobody is claiming to fully understand why this reorganization is happening. But the pattern, gathered across nearly 4 decades of unbroken data, is not something that can be waved away as noise. But if the sun's internal engine is running just as hot as ever, and its activity is simply relocating rather than disappearing, that raises an obvious question. If the surface can't be trusted to predict what the sun does next, how do we know when a cycle is actually going to end? That question, it turns out, has its own surprising answer. So here's the real question this video needs to answer. If 2 centuries of sunspot counting can no longer be fully trusted to describe what's happening inside the sun, how do scientists now explain the actual mechanism that turns extreme solar weather on? And, more importantly, off. You'd assume a solar cycle winds down gradually, the same way a storm exhausts itself over hours, gradually losing energy until it fizzles into calm. That's the mental model most of us carry. Even scientists carried some version of it for decades. It's wrong, and the way it's wrong is fascinating. New research presented at the Royal Astronomical Society's National Astronomy meeting in 2026 by researchers at the University of Warwick shows that severe solar storms and coronal mass ejections don't fade out slowly at all. They switch off abruptly, almost like flipping a breaker, at a very specific point in every cycle. Think of a treadmill slowly increasing in speed. You'd expect that if the treadmill were going to stop, it would gradually decelerate, giving you time to adjust. Instead, imagine it simply cuts out completely the moment the belt crosses one particular mark on the display. Every single time with mechanical precision. That's essentially the behavior researchers found hiding inside the sun's most violent storms. So, what actually flips that switch? This is where the sun's own rotation becomes the surprising culprit. The sun doesn't rotate uniformly like a solid ball. Different latitudes spin at different speeds. The equator completes a rotation faster than the regions closer to the poles. This is called differential rotation, and it's actually the engine that twists and winds up the sun's magnetic field lines in the first place, storing up the energy that eventually erupts as flares and coronal mass ejections. As a solar cycle progresses, the active sunspot regions responsible for the most violent eruptions gradually migrate away from the poles and drift toward the sun's equator. Researchers found that once these active regions cross below roughly 15 degrees of solar latitude, the differential rotation weakens sharply at that band. And without that rotational twisting, the magnetic field lines lose the tension needed to fuel major eruptions. The switch, quite literally, gets cut. Picture wringing out a wet towel. As long as you keep twisting both ends in opposite directions, tension builds and builds. But the moment you stop twisting, even if the towel is still soaked, the tension releases and nothing more builds up. The 15-degree latitude line functions almost exactly like that release point for the sun's magnetic tension. Cross it, and the twisting that fuels the most extreme space weather simply stops. Here's where this stops being abstract and starts being genuinely useful. Because this new switch-off model isn't just an explanation after the fact. It's becoming a forecasting tool. You'd think, going purely on the drama of recent years, that solar cycle 25 has already peaked and is now fading gently into history. It's true that cycle 25 dramatically outperformed the conservative predictions made before it started, driving historic geomagnetic storms. The widespread aurora displays seen across unusually low latitudes in May 2024, and a string of powerful X-class solar flares through late 2024 and into 2025 and 2026. But whether the cycle has genuinely crossed its switch-off boundary yet is still being confirmed, precisely because researchers are now watching that 15-degree latitude marker rather than just counting fading sunspots. And using this same switch-off framework, early forecasts for the next cycle, solar cycle 26, suggests something more moderate is likely coming, with a projected peak sunspot count somewhere in the range of 100 to 120, similar to or possibly slightly weaker than the cycle we're currently living through. That's not a wild swing in either direction. It's a sun behaving, on the surface at least, roughly the way it has before. But remember what we learned earlier in this video. Surface behavior and internal behavior are no longer guaranteed to match. The interior engine has been quietly reorganizing itself into a shallower, more compressed zone with every cycle recorded since 1987. So even a moderate cycle 26, judged purely by sunspot counts, could still be hiding an internal engine running at full intensity beneath an increasingly thin surface veil. That's the real tension driving this entire investigation. Two independent lines of research, one listening to the sun's internal sound, one tracking the latitude of its most violent eruptions, are both pointing toward the same unsettling conclusion. The sun's surface is no longer a reliable narrator of what's actually happening inside it. Let's take this to its most extreme, unsettling conclusion, because this is where the implications stop being about weather forecasting and start being about something much bigger. If the sun's magnetic engine really is compressing into a shallower and shallower layer with each cycle, and if that compression has been happening consistently across nearly 4 decades of measurement, then we are not looking at a temporary anomaly. We are looking at a trend, and trends, by definition, extend into the future. Nobody currently knows how far this compression can go, or what happens if it continues. Does the sun's magnetic engine simply stabilize at some new, shallower depth and continue operating from there indefinitely? Or is this compression itself a symptom of some longer, slower transformation in how the sun generates its magnetic field altogether? The kind of transformation that, on stellar timescales, could take thousands of years to fully play out, but that we happen to be catching the earliest fingerprints of purely by chance, using instruments that have only existed for the blink of an eye in the sun's 4.5 billion year life. Consider that unsettling scale for a moment. Bison has been listening to the sun for less than 40 years. The sun has existed for over 4.5 billion. If this compression pattern really is the beginning of a longer transition in how our star behaves, we are witnessing something equivalent to catching a single frame of a film reel that has been running since before Earth itself finished forming. And trying to guess, from that one frame alone, what happens next. That is either one of the great scientific privileges of being alive right now, or a reminder of just how little of the sun's true nature we've actually managed to observe, despite feeling its warmth on our skin every single day of our lives. So does any of this mean the sun is somehow becoming dangerous, or that its output is suddenly capable of reshaping our climate? Here, at least, the science offers something genuinely reassuring. Even across a full energetic solar cycle, the sun's total energy output, its irradiance, only varies by around 0.1%, roughly 1 watt per square meter. Translated into real-world terms, that accounts for less than 1/10 of a degree Celsius of variation in global average temperature. Long-term historical data confirms, clearly and repeatedly, that changes in the sun's overall brightness are not what's driving the warming trends measured on Earth in the modern era. That distinction matters because it separates two very different stories. The sun's internal architecture reorganizing itself in ways we're only just learning to detect, and the entirely separate, well-understood story of greenhouse gases reshaping our planet's climate. Those two stories should never be confused for one another, no matter how tempting the headlines make it sound. So here's what we actually know, and what we still don't. We know the sun's magnetic engine is being compressed into an increasingly shallow layer beneath its surface, cycle after cycle, based on nearly 40 years of listening to its internal vibrations. We know that the sudden, switch-like ending of extreme solar weather is tied to a precise latitude threshold in the sun's own rotation, not a gradual fade. We know cycle 25 outperformed expectations, and early evidence points to a more moderate cycle 26 ahead. Assuming the surface can be trusted at all anymore, which is precisely the question this new research is forcing us to reconsider. And we know that whatever is happening deep inside our star, it is not a threat to us, at least not on any timescale that should keep you up at night. What it is, instead, is a genuine scientific frontier, proof that even the object we've studied longer and more closely than any other star in the universe still has secrets buried just beneath its skin, waiting for the right instrument and the right 40 years of patient listening to bring them to light. The sun has been changing this entire time. We just finally built the tools quiet enough to hear it. And maybe that's the part worth sitting with longest. Not the compression, not the switch-off latitude, not even the forecast for the next cycle, but the sheer humility of the timeline involved. 4.5 billion years of solar history, and it took us until 1987 to even start listening properly, and until 2026 to notice the pattern hiding inside 4 decades of that listening. If a signal this significant was sitting there the whole time, quietly encoded in sound waves rippling through a star 93 million miles away, it raises an obvious question worth carrying with you long after this video ends. What else, right above our heads, have we simply not been listening closely enough to hear yet? If this kind of deep dive into the mechanics of our universe is something you want more of, make sure you're subscribed, because we're only getting started uncovering what's hiding in plain sight above our heads. Drop your own theory in the comments. Do you think the sun is settling into something genuinely new, or just having a quieter moment before its next storm? I'll see you in the next one.